Hello, everyone. It's me, Billy Younger, with www.youtube.com/Billy Younger Physics Solutions, with only the B in Billy, the P in physics, the first S in solutions, and and of course the Y in Younger capitalized. Anyways, you'll see that on my document in a second. But I'm here to use Gauss's law and show you how to properly use it, explaining all the details that's actually going on, and also I'm going to tell you, hey, all this work I'm showing you is just so you understand how it's going, how it's being done, but you're not supposed to show all this. You're just supposed to know that's what's going on. So hopefully this will be a very instructive Gauss's law problem for you. So let's start off by sharing my screen with you guys so you can see the actual problem that we're solving. Oh, that's not the one I want. Shared the wrong screen. Hold on. The one I wanted to share was this one. Okay, you see a solid metal, i.e. it's a conducting sphere of radius r and total charge q. In other words, when I do something like that in a problem, that means, or when a textbook author or teacher does something like that, that means you can assume you know r and q unless he or she explicitly later asks for r or q. So right now we're going on the assumption that we know r and q, and I am asked to find the electric field created by this conductor and graph its magnitude for all R values. Now, to make use of various coordinate systems, a sphere can be imagined as if its center is at the origin of a Cartesian coordinate system. Then various unit vectors, the I hat and the J hat, which are unit vectors pointing in the X direction and the Y direction, respectively. The rho hat, which is sort of like well, it's like in polar coordinates, basically the little r that you used in polar coordinates, where you just had an x and y plane, and you could also represent it as r and theta. I'm using that rho to represent that r because in spherical coordinates, the r actually has a k component as well. So that's what I mean by rho hat. It also has theta hat, which is a unit vector that points in the direction of increasing theta, both in polar coordinates. It's called the azimuthal angle, and it's in spherical coordinates as well as cylindrical coordinates, but both it only has x and y components. And phi hat is actually the polar coordinate for spherical coordinates, and r hat is the actual radial component vector for spherical coordinates. Again, I just use these because these symbols are handy, and if anyone's been introduced even slightly to the coordinate system through one problem or through looking them up on my YouTube channel, then I can use them and they know exactly what I mean, exactly which directions we're going. So for instance, the neat thing about rho hat is if you're on the y-axis, rho hat points in the j hat direction. It's identical to j hat. But if you're on the x-axis, rho hat is identical to I hat. But if you're, let's say, at 45 degrees counterclockwise from the positive x-axis towards towards the positive y-axis, and you're on any line there, then r hat would actually point 45 degrees from the x-axis, which is also 45 degrees from the y-axis, and would point away from the origin. So that just gives you a little bit of idea of what they are, so that you can get some sense. I'll just be using them, and I'll hand out the coordinates every now and then. Again, if you want to know more about the coordinates, you can just go to my YouTube site, Billy Younger Physics Solutions, and just do a search for cylindrical coordinates or spherical coordinates, and you'll find them. If you're not familiar with the coordinates, you can probably understand by just watching this problem being solved, or like I said, you can see those other coordinate systems. So we've seen the problem. I've actually written down the information on my tablet already, so I'm going to stop sharing that. You seem to know what's going on. We have a conducting metal sphere. I'm going to center it at the origin, and then I'm going to find the electric field everywhere. So now I'm going to share screen, this time with my trusty iPad / GoodNotes. So here's this, and now I'll have to do share my screen from the iPad. That should be done. So you notice I already wrote down the important variables, specifically R and Q. And I mentioned when someone says a conducting sphere of radius r and total charge q, you again assume that r and q are known. So what I'm going to do is I'm going to start with Gauss's law. And here's the solution. First off, Gauss's law says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. Now that left-hand side is specifically called the electric flux, and it's the electric flux because it has that closed circle on the integral, that actual oval that we're on top of the integral. That means you're only supposed to calculate that flux over a closed surface, and the closed surface is one that has a clear inside and outside. For instance, a toilet paper roll, a little piece of cardboard that is inside of a toilet paper roll, that is not a closed surface, because you could think, hey, I'm on the outside because I'm over here where the paper used to be, but you don't have to go through any cardboard to get on the inside of that tube. So that's not a closed surface. However, if you took the time and glued a circular plate on each end of that tube, then it would be a closed surface, because in order for you to go from the inside, which is, basically where the spindle that originally held the toilet paper was, to the outside, I'd have to cross either the cardboard tube, in other words, I'd have to go through the cardboard tube, or I'd have to go through one of the end caps. That's a closed surface. So that's what Gauss's law is on the left-hand side. It's calculating a quantity called electric flux, and flux is sort of counting of all the, in this case, electric field that is actually running perpendicular to that particular surface area. In other words, it has very little chance of being sort of bounced away, because it's going a little bit left and right instead of straight ahead. So that's what that is. And the dA is supposed to be a unit vector whose magnitude is the magnitude of the little differential area element, but whose direction is perpendicular to that little differential area element surface. So it's just a useful way of us defining a vector perpendicular to a little, sometimes rectangular, sometimes circular, all sorts of stuff shapes. And what Gauss's law says is that basically the total number of field lines penetrating a closed surface perpendicular to the surface, which is in some sense a measure of the electric flux, is equal to the charge enclosed over epsilon naught. So that's really what his law says. So let's get about drawing a coordinate system and using a Gaussian surface and applying Gauss's law. Now, this is a weird law in that Gauss's law is, unlike a lot of equations we use, which normally has you like saying F is equal to blah, 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 and you plug in blah, blah, blah and get out an F value. In this case, you're actually, in the way we're using Gauss's law, we're attempting to solve for the E, the integrand in that equation. So what I do is I work the left-hand side, and then I work the right-hand side of the equation, the left-hand side being the closed integral of E dot dA. And then I work the right-hand side, which is Q enclosed over epsilon naught. And when I'm done, I set them equal to each other and then use that to solve for E. The trick is you've got to, in order for this to work out so that you can actually extract that E from the integrand, you have to have certain symmetries. It is Gauss's law. It's not Gauss's helpful hint that sometimes work. It's Gauss's law, so it's always true. The problem is you can't always use it to extract the E, but it's still a law. You can always use it several other ways. Okay. So let me put my coordinate system down. I'm going to draw a coordinate system in black, and it'll have a z-axis, which I just drew. It'll have a y-axis, which I just drew, and it'll have an x-axis, which I just drew. So this is going to be my x-axis, this is going to be my y-axis, and this is going to be my z-axis. Now it's also going to have a sphere that represents the actual conductor. So let's say our conductor is roughly this big. I'm gonna let the computer make that a better circle, as it did, which is nice. Let's see if I can get it this way and move it just a little bit to make it look better. Okay, that looks pretty good. So that's our sphere, and that's our sphere whose radius is capital R, and whose total charge is Q. Okay, so that's the quantities we know. Now, I know from symmetry and from experience with Coulomb's law, which said that F, the force of Coulomb's law, is repulsive or attractive depending on whether the two charges are the same, in which case, in other words, the same sign, in which case they're repulsive, or in the case where the two charges have differing signs, then they're attractive. But in all cases, the force is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. But the key thing is the force acts along the line connecting the center of mass of the two objects. So you automatically get a line along which you know the force is parallel. It's just a matter of you deciding whether it's repulsive or attractive to put an arrow on the right end. So that's what we're going to make use of. So it seems to me, given that the Coulomb's law says that the magnitude of the force only depends on the charge, and inversely on the square of the distance between the point in question and the point that demarcates, say, the charge causing the electric field, then I know that an electric field due to a spherical distribution of charge should actually be a spherically symmetric electric field, meaning if I go out at any radius r from the center of the actual sphere, then that electric field will point radially outward. In other words, if you ran from the origin, which is where our center of the sphere is, if you ran from the origin to any point in question, the electric field would point along that line that ran from the origin to the point in question and would point away from the origin. That happens to be the very definition of the r hat vector in spherical coordinates. So that's why I'm going to make use of that. So far, all that symmetry that we know comes into play. I'm trying to get this thing to highlight again. Of course, it's not doing it because I want to move the sphere down a little bit. But anyways, what I'm going to do is I'm going to break this problem up into two parts. I'm going to first consider r less than r. So I'm going to say part one, because there's definitely a distinction for how much charge is going to be inside the metal for a given r. So right now I'm going to do for any r that happens to be less than big R. Okay, for that part, I'm going to make a hypothesis. I'm going to make a hypothesis using that symmetry that I just talked about. So the hypothesis is that the electric field E is actually going to be a function of R only, where R is literally the distance from the center of the sphere, which happens to be the origin, to the point in question. And that makes it seem exactly like what we expect with a spherical distribution of charge. And in fact, since it's a vector, I suspect it's going to point in the r hat direction. And again, that r hat direction is if you take any point in space and you connect the origin to that point in space, now you draw a line parallel to that line that connects it to the origin, and you have roughly something that's parallel or anti-parallel. You actually will have exactly something that's parallel or anti-parallel to r hat. R hat, in fact, will point away from the origin. So now you've got exactly something parallel, and its length is literally 1 unit, not 1 meter, not one anything else. It's 1 unit. In fact, you can even write out an equation for r hat in terms of theta, or actually in terms of I hat, J hat, and K hat. So that's our hypothesis right now, is that E of R our E, the E vector, is going to be only dependent on the distance r away from the origin, and its direction is always going to be in the r hat direction. So what we wish to do when we're applying Gauss's law is we're trying to create a closed surface that everywhere has either the electric field being constant on the surface, in which case it will be parallel to the dA vector. Okay, that's how the dA vector is defined, is the dA vector points outward from any closed surface, and it's perpendicular to the surface that has an area dA. Or the other option is, if I can't find a surface that on which E is a constant, and therefore E and dA are parallel, then I want E to be like 0 or perpendicular to dA. Okay, then that part of the flux through that surface integral, which is really what that left-hand side is, the flux for that surface integral is 0. So that's the big trick. I need to find a surface that is everywhere, has a constant E on the surface, or another way of looking at it, has a E that's everywhere parallel to the dA vector or perpendicular to the dA vector, because then that part's going to be 0. And what ultimately happens is you never, ever, ever actually do the integral on the left-hand side. You actually just know that the result's always going to become some electric field E, in this case E of R, times some area. So that's the big trick. So I'm going to walk you through all the details. What I've now made is a hypothesis about what I suspect the electric field is going to be. And now I've already decided that we were doing R less than big R. So I'm going to create a Gaussian surface. And this time the Gaussian surface is also a sphere. And its radius happens to be R, which is in fact smaller than big R. So right here, I'll draw this little line and say this is little r. Whoa. And say this little line is little r. So they're both spheres. So I could, for instance, draw like this to let you know that one's a sphere. And I could draw like this to let you know that one's a sphere. I could even do something like this to remind you it's a sphere. So that is an actual sphere. Now, what I need to do is I need the left-hand side of Gauss's law. And the way I write that is I write LHS. And then I write the closed integral of E dot dA. Okay, that's the left-hand side. But I need to figure out what dA is. Now, dA has to be a little differential area element on the surface of your Gaussian surface. So this red thing is what I call it, a Gaussian surface. And the reason I chose it is you see that the dA vector for this is everywhere radial, which is in fact exactly everywhere parallel to E. So if you really wanted to know what a patch of it would look like, you could actually take the time and study cylindrical coordinates, or excuse me, spherical coordinates, but you really don't have to. All you know is there's some differential area element dA, and that a line perpendicular to that little area is in fact in the r hat direction. So I'm going to call this dA vector. Now in spherical coordinates, technically that dA would be r, the radius, times the cosine of theta, d theta. That would be the length of the bottom / top edge. And then the other side, I'd multiply it by to get the rectangle, because we're treating it like a rectangle. The other side would just be r d phi. So that's technically what's going on here. That if you happen to know cylinder or spherical coordinates or double double integrals and stuff like that. That's really what's going on there. But the beauty of Gauss's law is I don't have to do that. I just have to call it dA and realize that it too points in the r hat direction. So the left-hand side, and I'm sorry it's taken so long, but this is just me trying to explain it. The left-hand side becomes the integral of E of r hat, dotted with the dA r hat, and it's on the red sphere, on the Gaussian surface, whose radius, of course, is r. Now, since its radius is r, that E of r is truly a constant, so I can really just pull it out in front and know that's E of r times the integral. And here's the neat thing about dot products, which is what that little dot in the integral is. The dot product is what we call a linear operator. So I can pull that dA that's in between the dot and the second r hat, I can pull that right out in front. And then all I have left is r hat dot r hat. Now, you might recall that, let me go on a sidebar here. I will go with a unique color. I will go with gross orange. A dotted with B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So r hat, and this goes for any vector with that little hat on top, has a magnitude of 1. So in the case of r hat dot r hat, I have 1 times 1 times the cosine of the angle between them. Well, they're identical vectors, so the angle between them is 0, and of course the cosine of 0 is 1. So I can immediately recognize that this r hat dot r hat is in fact just 1, and what I get is an integral. Remember, it's still over a Gaussian surface that happens to be a sphere. I get E of r times the integral of dA, which is obviously just A. So what's the area of a sphere? Well, the surface area of the sphere is 4 pi r squared. So that's actually the left-hand side. So notice I got an electric field times some area. That's always what you're going to get on the left-hand side of Gauss's law when you're using it this way to extract an integrand. It's either going to be E times some area plus E times some area plus 0, or all E times some area or something like that. It's never going to be anything more complicated. You never actually have to physically do the integral. You just have to realize, hey, the integral of dA, according to the fundamental theorem of calculus, is A. And then you say, well, what was A? Well, A was the surface of a sphere. And I know that the formula for the surface area of a sphere is 4 pi r squared. So it will help you, obviously, to know the area formula for the surface of a sphere, the volume formula for the volume of a sphere, the area formula for the surface of a cylinder, and the volume formula for the volume of a cylinder. Those all come in handy. So I've now done the left-hand side, and now I got to realize, well, what fraction of the actual charge Q is going to be inside that Gaussian surface? So let's start now with our right-hand side. The right-hand side of Gauss's law is, in fact, Q enclosed over epsilon naught, which equals 1 over epsilon naught. Now, here's the big deal. It turns out with conductors, and this is sort of the definition of a conductor. The definition of a conductor is a material whose charges, like the electrons, are sort of loosely attached to their mother atom or their mother molecule. And those loose charges, again, which more or less are the electrons, because the atoms are too big and the nucleus is too massive compared to it. But the electrons will be wobbling and running all around throughout the area. Well, if you have a bunch of like charges, they all want to get as far away from each other as possible. So it turns out when you put a charge on a conducting sphere, all the charge will in fact propagate outward until they're all the maximum distance apart, which means they'll locate themselves smoothly all over the entire outer surface. Meaning if I took a 1" by 1" rectangle, that's slightly curved because it's the surface of a sphere. If I took a 1" by 1" section of that sphere and determined the charge in it, I would get a number of coulombs. If I grabbed any other 1" by 1" square anywhere else on that sphere, it would give me the exact same number. And even if I grabbed any millimeter by millimeter square and found the charge in it, divided by a millimeter per times a millimeter, and then converted the millimeter squared in the bottom to inches squared, I would still get the same number. So that's ultimately what's going to happen. And because of that, Q enclosed is actually 0. So I'm going to say Q enclosed is actually 0 because charges are free to move, so they all get as far from each other as possible. And that implies uniform surface charge. And you might even call that uniform surface charge sigma, which would be a certain number of coulombs per unit area, which obviously in this case, we know the total coulombs is Q, and we know the total area is 4 pi big R squared. So sigma would actually be equal to Q over 4 pi big R squared. So for this first part, I'm now going to say left-hand side equals right-hand side. And that's going to give me E of R times 4 pi R squared is equal to 0, which means E equals 0 for R less than big R. Okay. So now I have to do the next part, which I'm going to call part 2. And that's for R greater than big R. Okay. So I'll draw a new Gaussian surface. And my Gaussian surface will be red again. Its radius will be R again. Only this time it's R greater than big R. Okay. And again, I can make some marks on the red just to make sure you know that that red Gaussian surface is a sphere as well. So this is the Gaussian surface again. Okay. Now we saw how everything played out. Our hypothesis is still the same. So I'm going to say hypothesis is that E is equal to E only a function of R, which is a distance from the origin, which is a distance from the center of the sphere, which really matters, times R hat. The dA is going to be exactly the same thing. So the left-hand side is going to be the closed integral of E dot dA over, again, the Gaussian surface, which is going to equal the integral of E of R hat dot dA R hat But again, this is a linear operator, plus we're evaluating this at r equals the constant radius of the Gaussian surface. So E of r is a constant. So I'll get E of r out in front, and I'll get the integral of dA times r hat dot r hat, which we know for a fact is just 1. So ultimately, I get exactly the same thing I had before, E of r times 4 pi r squared. Okay, so that is our left-hand side. Our right-hand side is a little more complicated, but really is pretty simple. It's the right-hand side is just equal to the charge enclosed, and that means inside the closed surface over epsilon naught. Well, we know for a fact that the total charge of this sphere is in fact Q. And we know that the Gaussian surface with radius r greater than big R has all that Q inside of it. So the answer is just Q over epsilon naught. Then all we have to do is set left-hand side equal to right-hand side, and we get E of r times 4 pi r squared is equal to Q over epsilon naught, which gives us simply E is equal to 0 for r less than big R, and it's equal to Q over 4 pi epsilon naught r squared r hat for r greater than big R. Okay, you can see obviously when I solve for E of r, that's just going to be E of r is equal to Q over 4 pi epsilon naught r squared, and that's exactly what we got. I'm going to zoom in on that a little bit and try to clean it up just to make it look a little better. I've got my eraser out. Things are getting real now because I've got my eraser out. Ooh. So now I'm going to say the electric field outside is, of course, Q over 4 pi. Whoa, that's really bad. 4 pi epsilon naught r squared r hat. And this is for, oops, don't have to do that part. And I'm going to say this is for r greater than big R. So this is a component of the electric field that happens to be, of course, electric field that happens to be perpendicular to the surface of the actual charge distribution. In other words, the electric field is radial, and the surface, of course, is perpendicular to radial because it's a sphere. And it turns out there's a rule that basically says the perpendicular component of the electric field, perpendicular to a surface, as it crosses from one material to the next, is continuous unless there happens to be a surface charge. If there's a surface charge, then it turns out to be not, in fact, continuous. It differs by an amount sigma over epsilon naught. So now if I actually take the time to make a graph of the magnitude of this electric field for all r, I can do that as follows. So let's draw a quick coordinate system. So here is the electric field axis, and here is the r axis, and this quantity right here will be big R. Now, what the electric field says, according to this piecewise function, is the electric field is going to be 0, and then it's going to jump up to, let's say this value is Q over 4 pi epsilon naught big R squared. Okay. And I can dot it to make sure I keep it on the same line, basically right there. And at that point, the electric field has a giant discontinuity, and it goes down like this. So this part is proportional to 1 over R squared, like we saw before. Now, the neat part is this quantity right here is the discontinuity, and you can see it is sigma over epsilon naught, because sigma is Q over 4 pi R squared, and epsilon naught is down there already. So you can see, in fact, that the discontinuity is exactly sigma over epsilon naught, which is what I claimed. So we've now solved a Gauss's law problem for a conducting sphere of radius r and total charge q. I've even managed to solve it over all space and give a plot of the magnitude as a function of position. Of course, the final answer really is this quantity, which I should box off just to make clear exactly what the answer is. So that's the answer, and we learned about the discontinuity. Now, as I was telling you, when you actually are practicing this, the left-hand side is always going to become E times some area. There might be two terms, E times some area plus E times the same area, or E times some area plus negative E in parentheses times negative A in parentheses, plus 0, plus 0, plus 0. That's always what the left-hand side is going to be. If you find yourself not getting that, then you've probably done something wrong. And of course, a lot of times it's not just A, it has to be, for instance, in this case, the A was the actual surface area of the Gaussian sphere, which in part 1 and part 2 was both 4 pi r squared, because that is the surface area of the sphere. So hopefully that helps you further understand Gauss's law a little bit. We are technically doing a surface integral on the left-hand side. If you want to learn a little bit more detail about how a surface integral is handled, that's normally not taught until Calc 3, and a lot of Calc 3, maybe most Calc 3s never get to that. But you can look on my YouTube channel. I have one specifically called A Long, Tedious, but Useful Surface Integral. Honestly, though, all you have to do is do a search for surface, and you'll find me doing an integral, a surface integral. So I hope that helps. Feel free to email me. As you can see on the description of my video, you can see what my email address is, and you can email me and ask me for any given video's title, and I will send you the good notes in PDF form, or even photographs of the handwritten notes that I did in some of the older videos. I hope that helps, and I hope you all tell people about www.youtube.com/Billy Younger Physics Solutions, with the B, the Y, the P, and the S capitalized. Thank you.